You know, Plankton's been trying to steal the secret formula for decades now. He's been doing it all wrong. The secret formula was never just an ingredient list. It was actually calculus. By using the 3D concepts of quadratic surfaces, we not only fully analyzed each individual structure of the Krabby Patty, we configured it to perfection. Let me take you on a journey of mastering the recipe of the beloved burger of the Bikini Bottom. The best way to master the art of cooking is to know the basics. Here is a quick review of quadratic surfaces and their formulas in this image right down here below. In order to represent buns, tomato slice, and patty, we'll use an ellipsoid. Next, we'll use the parametric plane to represent a cheese slice. And lastly, in order to represent the lettuce waves, we will use hyperbolic paraboloids. Let's start with the top bun. In order to achieve that round ovally shape, we want to use the equation of an ellipse, which is in the form of x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. To make it look more realistic, we can manipulate the coefficients a, b, and c. Increasing a and b stretches the bun sideways, while decreasing c flattens it slightly so it's not too tall. By adjusting these values carefully, we can get that perfectly golden top bun shape. Next, we want to do the same for the bottom bun, but arranging the ellipse so that we only use the bottom half. Every good burger has to be balanced out with the right amount of greens. Now we want to construct the perfect, crispy and wavy piece of lettuce. To get that natural ripple, we use the equation of a hyperbolic paraboloid in the form of 0 over c equals x squared over a squared minus y squared over b squared. This surface naturally curves up in one direction and down in the other, just like the folds of real lettuce. By adjusting the coefficients a and b, we can control how deep or shallow these waves are. Smaller values create sharper, crunchier folds, while larger ones give us a gentler, leafier look. With a few quick changes, we can serve up a mathematically perfect piece of lettuce. Moving on, we have the tomato slice, which we are going to represent using an ellipsoid. Tomato slices are very thin. In order to convey that in an ellipsoid, we will have a very small coefficient c. In this case, our coefficient c is 0.0225. And in a graph, this shows a very thin slice, as you can see on the screen, which is perfect for representing a tomato slice. In order to make sure that the tomato slice sits exactly between the ingredients that we want it to, we replace z squared with z minus 1.15 squared. This will shift the entire ellipsoid up to be centered at z equals 1.15. Moving on, you can't forget about the cheese. By constructing a flat plane, z equals k parallel to the other ingredients of the burger, we can represent that perfectly melted slice, where k is a constant that sets the cheese's exact height between the patty and the bun. By adjusting the value of k, we can position the cheese right where it should be, not too close to the patty so it doesn't melt too much, but just enough to make it perfect. It may be the simplest part of the Krabby Patty, but it is absolutely crucial to get it right. Lastly, we have the heart and soul of a Krabby Patty, the patty itself. Again, we want to start off using the basic structure of an ellipsoid. We want our patty to be the perfect thickness, which we do by ranging z between small positive and negative values. We slice off the top and bottom to get a nice, even layer. And there you have it, our own Krabby Patty burger, with our ellipsoid making the top and bottom bun, our lettuce slice being represented by a hyperbolic paraboloid, our tomato slice being an ellipsoid, cheese being a plane, and our patty being a ellipsoid. Congratulations! Now you have officially entered Math Chef mode. We're going to tweak equations to get the perfect shape. Think of coefficients like seasonings. Adjusting A, B, and C changes the taste of your graph. Restricting domains is like slicing your ingredients to just the right portion. Shifting the center is like placing each layer neatly on top of each other. Now let's step back and see how all this ties into Calculus 3. In this course, we use various quadratic surfaces to sketch out layers of burgers. Understanding how these mathematical properties interact helps us see geometry not just as a shape, but as a living, changing system. The Krabby Patty becomes a 3D model of how calculus describes the real world. Now it's your turn to master the secret formula. Using our interactive Desmos setup, you can pick your ingredients, change your coefficients, and build your own Krabby Patty. Watch how each mathematical tweak reshapes your creation and enjoy being a math chef. So I guess now you know the secret formula. It's not ketchup or pickles, it's calculus. From the curve of the bun to the ripple of the lettuce, calculus does every part of the job.